Welcome to this mini lesson on inverse trigonometric functions. Recall some basic facts about functions that you would have learned in algebra. By definition, a function is a relation, a set of ordered pairs, in which each element of the domain is paired with exactly one element of the range. An equation f is going to be a function if and only if its graph passes the vertical line test. I'm sure you remember that from algebra. And another thing you would have learned was how to algebraically and graphically find the inverse of a given equation. Every equation is going to have an inverse. The issue becomes, is that inverse a function also? Right, that's the big question. You might remember the different methods by which you found inverses. Graphically, if you just have a set of points on a function, you just flip-flop the x's and y's, regraph the points, and connect the dots. That's how you find an inverse graph of a function. Algebraically, you might recall you would take the original equation you're given, flip-flop the x and the y in the equation, and rearrange then to solve for y. Inverse trig functions are going to behave very much the same way, and the same issues arise as we saw with algebraic functions, and whether their inverses are functions as well. So consider what the graphs of sine, cosine, and tangent look like, as well as their domains and ranges. We're going to use this as a launching point for our discussion about inverse trig functions. We're really going to concentrate just on the three main trig functions. Of course, you can do inverses of secant and cosecant and cotangent. They are not given primary treatment, though, in the traditional AP calculus curriculum. So that's why we're concentrating really just on sine, cosine, and tangent. So we're going to consider what the graphs of each of the original functions look like, and then what the inverse graph looks like, that idea of flip-flopping the x's and the y's and redrawing the graph. And we're going to talk about if those inverses are functions themselves. So let's start with sine. Here you see a graph of the sine curve. You'll notice the x values are your angles, y values are your actual sine values. Remember that sine is limited in between -1 and +1. You can almost think of the unit circle. That's where that comes from. You know, they're tied together. Really, the unit circle comes from this curve. It's the idea, they often refer to the unit circle as the wrapping function, because if you took this curve, like one period of the sine curve, and wrapped it around to make a circle out of it, that's where the unit circle values come from. So in terms of the domain and the range of the sine function, the domain is all real numbers because it keeps going in the positive direction and negative direction. Really, you can take the sine of any angle at all. Doesn't matter how big, how small. The range, however, is always confined to in between -1 and +1. If we were to take this sine curve and create from it the inverse graph, what we would do is take every single one of these points you see, flip-flop the x's and y's, redraw it, and what we come up with is this. All right, now notice a few things about this. Notice now on the x-axis you have those values in between -1 and 1. Right, that's one of the ideas that carries over from the inverses of algebraic functions. Remember how the domain and the range flip-flop? The x's become the y's. What used to be the y's are now the x's. Along the vertical axis, the y-axis, now you notice the angles. You got the negative angles down here underneath the x-axis and the positive angles up top. So if you take a look at this, this is what the inverse sine curve actually looks like. But obviously it's not a function, because if you pick any x value, like pick one right here, just a little shy of 1, all right, it has infinitely many y values to it. All right, so the way in which the inverse curve looks here, it is not a function. That's the problem. Because what we want to do in mathematics, we like things to be functions. So the idea is we're going to take this and restrict it somehow, look really just at one piece of this inverse curve, And it's from that that we come up with the inverse sine function. All right, so let's take a look at it and consider how we might want to do this. All right, we only want one little chunk of this curve as we see it. All right, now ideally we'd want to include both positive x's, negative x's, positive y's, negative y's, so we want to include a little bit of everything. So the way in which mathematicians really restricted this was to look simply at the part from here. Try to draw it for you. So starting here, this little part right in here in the middle. All right, so notice how the angle value that it starts out is negative pi over 2, and it goes to this point here, which is a positive pi over 2. But notice how we're including negative values of y, we're including positive values of y. So this little piece right here is what the actual inverse trig function looks like. It's really just a restriction on the total inverse sine curve. If you were to go on your graphing calculator, let's see, and actually ask the calculator to graph the inverse sine function, you'll notice how it looks exactly just that piece I highlighted. See? It's just that one little segment. Notice it doesn't even give you the entire curve. All right, so if you take a look at just this little piece, and from that we want to come up with what the domain and the range would be for the inverse sine function. All right, so the domain, remember that's our x's. It goes from -1 to +1, and it does include those because, you know, here's these points here. The range is the y values, which in this case becomes the angles. And notice what angles it extends from negative pi over 2 to a positive pi over 2. So this is the part that actually you're going to need to know, this part right here. This is going to be really important for you to know. In terms of the notation you're going to see, we refer to this function as, there's two different notations. The one that you probably know from your calculator, sine -1 of x. That's very much in keeping with the traditional notation for the inverse of an algebraic function. I'm sure you're familiar with that notation, f -1 of x. Okay, that's really in keeping with that type of notation. That notation of sine -1 of x, and the same holds true for cosine and tangent, that dates back to about the early 1800s in England. It was the British mathematicians that really started using that notation, very much to be in line with the traditional notation that you see for the inverse of an algebraic function. The other notation, however, is what we refer to as arc notation. So for the sine curve, it would be arc sine of x. Where that comes from, that notation actually dates back farther than the sine -1 of x. The arc function notation dates back to about the late 1700s with French mathematicians. The reason they came up with that, and I think you guys will agree, you know, look at what you're looking at here. It's just really one arc of the entire curve. All right, that's really where that notation came from. You will see both interchangeably in our course and really any AP Calculus course. In college and on the AP exam, they do use both the notation. So you do want to be familiar with, think of them as synonyms, really. It's just two different ways of expressing the same thing. Each kind of conveys a different aspect, I guess, perspective on this inverse trig function curve idea. All right, but as I noted out of that, the big thing you're going to need to know later on is the range part of that. All right, so I'll show you later on how that feeds into the problems we'll be solving. So let's look now at cosine. Oh, okay, we're going to start to fill out this little chart first. All right, so recap, we're going to just summarize what we had. The domain for the inverse sine function was -1 to 1. The restricted range becomes from -pi over 2 to +pi over 2. So think about what quadrants that would be, because this is something else that will help you out later on. If you think of, and maybe think of the unit circle if you want. Start at the bottom at negative pi over 2, and you go counterclockwise up till you reach the top of the circle. You've passed through quadrants 4 and quadrant 1. All right, again, these are all little bits and pieces that will help you out to solve and evaluate inverse trig expressions later on. All right, let's do cosine next. So here we have a picture of the cosine curve. Again, domain is all real numbers, range is -1 to +1, exactly as it was for sine. So what we're going to do is create the inverse cosine curve by taking every one of these points. Once again, we're going to flip-flop the x's and y's, redraw the graph, and when we do that, we have this. All right, notice how it looks a heck of a lot like the sine curve. All right, just shifted a little bit. And just like we saw before, we want to restrict this because as it appears now, obviously it's not a function. So the way in which mathematicians, that once again, they kind of figured, all right, well, we want to take care of both positive and negative x's. It would be nice to have negative angles and positive angles, but in this case, it kind of doesn't work out very easily that way. So the way in which this one got restricted was to start here, over here at +1 on the x-axis, and it goes up through pi. All right, once again, it's just one little arc, one little segment of the entire inverse cosine curve. Again, if you were to go back to your calculator and ask your calculator to graph that, maybe I'll zoom in a little bit. Nope. All right, that was the sine curve. Let's do cosine. Inverse cosine. All right, and there's that little segment that we saw. Remember on your calculator here, the little hash marks that you see along the x-axis, they do not correspond to like 1, 2, 3, 4. So just keep that in mind, okay? In case you're wondering. So let's get from this the notation that we're going to see, all right? The way in which we represent this function, as your calculator does it, you know, cosine inverse, that's our, or inverse cosine, that's how we would read that. In terms of the arc function we talked about with the sine curve, it would be arc cosine of x. So notice the domain and range of this. The domain for the x's, once again, it's going -1 to +1, inclusive. And the range, which are our y's, notice how this is going from 0 to pi. But in doing that, notice how you're taking care of, you know, negative cosine values, you're taking care of positive cosine values. So pretty much you got all your bases covered, basically. That's kind of how they came up with these. Once again, it's going to be this range part that you really need to know. So let's go back to that table and fill that in. So domain was from -1 to 1. Restricted range went from 0 to pi. So again, if you consider what quadrants that covers, think of the unit circle starting at 0, and you're going to go clockwise over to pi. So in doing that, you've passed through the first quadrant and the second quadrant. So the last one to consider is tangent. So here's your tangent curve. Remember, this is the one that looks very different. Lots of asymptotes, pretty much at multiples of pi over 2. You can see that expressed in the domain. The domain is all real numbers except pi over 2 times n, where n is an odd number, integer specifically. And if you take a look at where the asymptotes are, notice how it's over here at like -1 pi over 2, it's at +1 pi over 2, then 3 pi over 2, 5 pi. Notice how they're all odd numbers in the numerator? That's where your asymptotes are going to lie. And your range is all real numbers in this case. Remember, tangent values, we get those from the y value over the x value. You can really have, tangent values can get really big, they can get really small, depending upon what angle you're dealing with. So if we wanted to come up with the inverse tangent curve for this, again, we're going to take every one of these, we call these branches, all together they collectively make up the tangent curve. We're going to take the points on each of these branches, flip-flop the x's and y's. Pretty much now our asymptotes are going to go horizontally now. And our curve looks like that. That's what the inverse tangent curve looks like. So notice where your asymptotes are now. All right, they're all horizontal. They're still at, increments of pi over 2. All right, so like this one right here that's a positive 1 pi over 2. This would be 3 pi over 2. The one at the very, very top here is 5 pi over 2. So in terms of restricting this, again, looking at it here, it's obviously not a function. The way in which mathematicians restricted this, you can probably figure out yourself. They went easy, and they went the one in the middle, right here, that passes through the origin. All right, again, you have both negative x's and positive x's covered. You have negative angles, some positive angles. You got a nice mix of both. So the notation we'll see for this, and you can graph this on your calculator if you like, inverse tangent of x, or you'll have arctangent. So the domain now, remember the domain and the range flip-flopped, and remember the range up here was all real numbers, so now our domain is all real numbers. Hopefully you're familiar with that symbol for the set of real numbers. The range then, and remember we're just talking this one in the middle here. All right, so it is sort of going, because this one right here, where this horizontal asymptote is, that's negative pi over 2. This first horizontal asymptote, rather, that lies above the x-axis, that's at positive 1 pi over 2. But notice you can't equal either of those because they're asymptotes. So the range in this case goes from negative pi over 2 to positive pi over 2, but they are open intervals because they do not include those endpoints. So if we go back to that table that I had that I was filling out, our domain is going to be all real numbers. Restricted range, notice how it's kind of like the inverse sine, except it does not include the endpoints. It's still passing through those same two quadrants. If you start at the bottom of the circle at negative pi over 2 and go clockwise up through 0 to positive pi over 2 at the top, you've once again passed through quadrants 1 and 4. All right, so I've been saying all along that it's these restricted ranges that you need to know, because that's what you're going to use when you evaluate inverse trig expressions. All right, with inverse trig expressions to evaluate, you have to remember you're looking for the angle with the given trig value. Like I like to say, you're playing Jeopardy. You're told what the trig value is, you have to say what the angle was. So it literally is going backwards from what you've done up to this point. It is customary by definition, due to these restricted ranges that we just looked at, to always do inverse trig functions in radians. So if by chance you were doing these on your calculator, you would be in radian mode. It's also for this reason that we concentrate on problems related to the unit circle. So your answers, your angles, are going to be in terms of pi. All right, so I have several examples for us. And let's start with this one that I've kind of written out for you. So for instance, if you have inverse sine of 1/2, that's how you read that. What that means is you're looking for the angle whose sine value is 1/2. Like I said, you're playing Jeopardy. You're used to doing before, what angle has a what sine of what angle is 1/2. All right, that's kind of, or you're asked, okay, sine of some angle, what is the trig value? All right, you're literally going backwards. So this value here, That's the actual sine value. Your answers are going to be angles. And where that comes from is going back to what those restricted ranges were. Remember, they were always angle measurements. So when you're evaluating inverse trig functions, you're looking for an angle. Now, where these restricted ranges come in, all right, yes, we are looking for an angle whose sine is a half. Well, think of your unit circle. And we know from before, there's two places where sine would be a positive a half. It could be up here in the first quadrant, or it could be over here in the second quadrant. But remember the notation here, inverse sine, it has to be a function. There can only be one answer. There cannot be two answers like we used to have with trig equations. All right, so what you're really doing is, by virtue of the fact of how the notation is, that is your indication. You are dealing with functions, therefore you can only have one answer. That answer is coming from what those restricted ranges were. All right, in this case, the restricted range for inverse sine was in between negative pi over 2 and positive pi over 2. Remember how I told you to think of the quadrants? So because of that, the only one answer we're going to get has to be up there in the first quadrant. We're not even going to think about the second quadrant answer. So in this case, your answer for inverse sine of a half is going to be pi over 6, because that's the angle in the first quadrant that has a sine value of a half. So you can see how you're using all your unit circle stuff and your ordered pairs. That's why you have to know those really well. All right, let's look at a cosine example. So if we have our cosine of negative root 2 over 2, that means we're looking for an angle whose cosine is a negative root 2 over 2. Well, let's think of it from the perspective of the unit circle again. All right, if we're talking an angle whose cosine is a negative root 2 over 2, we know cosine's negative over in either the second quadrant or third quadrant. But because it's the arc function, it can only have one answer. That answer is coming from the restricted range, from 0 to pi. So you're only considering from 0 to pi. So that means our answer has to be in the second quadrant. So the answer for this would be 3 pi over 4. All right, so these definitely become problems you do in your head. We're going to work through a few of them. We can draw pictures if you find that helpful. You'll probably get to the point you don't have to. But starting out, it's not a bad way to visualize it. But you really, really need to know those restricted ranges. All right, because that's where your answers are going to come from for each of these problems. All right, so let's try a few. Suppose we wanted inverse cosine or arc cosine at a negative a half. All right, so we can draw pictures to start if that helps you. So you figure cosine has to be a negative. So we know that would happen either over here in the second quadrant or in the third quadrant. But because it has to be an inverse function, because of the arc function, remember, restricted range for inverse cosine goes 0 to pi. So the only answer we're going to have comes out of the second quadrant. The angle over there that has a cosine value of a negative a half is going to be, think of your unit circle. Remember, cosine is your x-coordinate. So you can think reference angle if you want. All right, reference angle whose cosine is a half, the x-coordinate has to be a half. That's going to be pi over 3. So your answer for this one is going to be 2 pi over 3 because it has to be over in the second quadrant. And notice how the answer looks. It's not x equals anything. There is no x. In this problem, it's not an equation. It's just an expression you're evaluating. So you just have arc cosine of negative a half. It's 2 pi over 3. You can't go turning these into equations if they're not given to you that way. All right, how about inverse cosine, or inverse tangent rather, of 0? All right, well, this is probably going to be a quadrantal one because tangent is 0. But think about where the restricted range is for the inverse tangent function. All right, it has to go from negative pi over 2 up to pi over 2. So you're kind of starting down here at negative pi over 2. You're going through 0 up to positive pi over 2. Think of it as almost like a number line, linearly. So you want to know where in there is tangent 0. Well, the only place that's going to happen is over here. All right, remember tangent you get by doing y over x, so you have 0 over 1. So this is simply 0. All right, we do not call it 2 pi. To call it 2 pi would be wrong. Remember how the restricted range, it goes from negative pi over 2 to positive pi over 2. Your answer has to lie in there. 2 pi does not lie in between negative pi over 2 and positive pi over 2. That's why if you were to say 2 pi, that is wrong. It has to be 0. All right, let's try a couple more. Arc sine of a negative root 3 over 2. All right, so thinking about what that might look like. Sine is negative down here in third and fourth quadrants, so down here. All right, but remember, since it has to be a function, we have to consider that restricted range. So that goes from negative pi over 2 up to positive pi over 2. So the only answer we're going to have is down there in the fourth quadrant. All right, so you can think of your reference angle. Think of your unit circle. You want the angle where the sine value, the y-coordinate, is 3 pi over 2. So you can think in terms of reference angles if you find that helpful. All right, so that reference angle, it's going to be pi over 3. All right, but you need to be in the fourth quadrant. Now you can't say your answer would be, if you did like 2 pi minus pi over 3 and you get 5 pi over 3, that's wrong. Because remember your restricted range, it has to lie in between negative pi over 2 and positive pi over 2. So the answer for this, you're just going to use the negative angle. It's actually less work than what you had to do before when you solved trig equations. And that's really going to be true for all your answers with inverse trig expressions that lie in the fourth quadrant. They're simply going to be the negative of the reference angle. Again, if you were to say 5 pi over 3 is the answer for this, what I would tell you is like, okay, well, you got the right idea. You're in the right place. You're in the right quadrant, but you named it incorrectly. All right, so you have to make sure you're naming it correctly. It would be negative pi over 3. All right, how about arctangent of negative 1? Remember, it's really, hopefully you do have your tangent values memorized because it kind of does help. All right, so let's think about tangents negative in second quadrant and fourth quadrant, but restricted range, remember, goes from negative pi over 2 to positive pi over 2. All right, so our one answer for this is going to be down there in the fourth quadrant. So you want to think, all right, one angle from the unit circle has a tangent of 1. That's going to be pi over 4. And we want to be down there in the fourth quadrant. So our answer is simply negative pi over 4. Again, if you were to do something like you would have done with trig equations and done it as 2 pi minus pi over 4, so you would have gotten 7 pi over 4, that again would be wrong. Okay, again, I tell you, you're in the right place, you got the right idea, but you named it incorrectly. All right, so I think these are the last two I have for you. All right, so inverse sine of square root of 2 over 2, also known as 1 over root 2. All right, so we're talking about sine being a positive square root of 2 over 2. So sine is positive, we know, either in the first quadrant or the fourth quadrant. But we have to consider our restricted ranges. So that goes from negative pi over 2 to positive pi over 2. So the only answer we're going to have is out of the first quadrant. So think of your unit circle. You want to think of where the sine value, the y coordinate from the unit circle, is a square root of 2 over 2, known to most of us as 1 over root 2. That's simply going to be pi over 4. And finally, the last one, inverse cosine negative root 3 over 2. So cosine is going to be negative in the second and third quadrants. So over here or over here. But restricted range for inverse cosine takes us from 0 to pi. So our only answer is going to be there in the second quadrant. So you want to think, again, you can do a reference angle if you find it helpful. So from your unit circle, you want to think of the angle where the cosine, the x-coordinate for the point, is a square root of 3 over 2. All right, so that reference angle is pi over 6. All right, we want to use that to get our answer out of the second quadrant. So if you can really do exactly like you did do the trig equations. You can do pi minus pi over 6, and you get 5 pi over 6. Right? Because remember, the angle answer you give has to be in between 0 and pi, and 5 pi over 6 is in between there. So this very much becomes a great exercise in mental gymnastics, using your, all your trig unit circle knowledge, as in terms of which trig functions are positive where, in terms of your unit circle ordered pairs, in terms of reference angles. It's a great mental exercise to do these. And you should become very adept at doing these. You will see these throughout AP Calc, either in this form or as a trig equation. You'll see them in both forms. So you very much want to be able to, adapt to either one and be able to answer both types of questions. So hopefully this lesson helped you understand inverse trig functions a little bit more, and you'll find them a little bit easier to work with as we move forward.